Let's now use our recently acquired knowledge about Bessel functions, Neumann functions, Hankel functions to do something interesting, and that is calculating the eigenmodes of an optical fiber. Now, an optical fiber, as you know, has a cylindrical cross-section. So you have a circular core with a refractive index N1, which is bigger than the refractive index N2 of the cladding. Let's say that the radius of the core here is capital R. And what we're interested in is eigenmodes. So these are field profiles that propagate perpendicular to the plane of the cross-section here. So something that propagates along the z direction. So let's try and find these eigenmodes, which means solving Maxwell's equations, which in our case means solving Helmholtz, the Helmholtz equation. And we're going to restrict ourselves to the scalar Helmholtz equation, because otherwise it's going to be a little bit too painful. So let's solve the scalar Helmholtz equation. And let's just assume that for our field, which is in general a function of our three coordinates here in the cylindrical coordinate system, is that for our field we will assume a following form. We're going to say that the R dependence is only concentrated in this capital R function, where I apologize for using the same symbol here for two completely different concepts. I guess you're clever enough to make the distinction here. And then we're going to introduce the following dependence on theta and z, which is exponential minus j k theta theta exponential minus j kz z. So now that we know what we're interested in, we can also give a physical interpretation behind these two terms here. So pause the video and see if you can find what the meaning is behind those terms, what the meaning is behind kz and k theta, and also see if there's any additional constraints that you would like to impose on this k theta here. So pause the video and have a think. The goal of the problem is to find eigenmodes of an optical fiber, of a waveguide. Now, what's the definition of an eigenmode? It's basically a field profile where the stuff that happens in the transverse direction stays constant and does not depend on the propagation direction z. And the only thing what happens in the z direction is this complex exponential here. So by the very definition of an eigenmode, this is why we have this vector here. And then kz obviously is the propagation constant of the eigenmode. We also introduce something similar in the theta direction. So it's a little bit like propagation along the theta axis here. But here it's a little bit more subtle because of the physics of the problem. Well, we know theta varies between 0 and 2 pi physically, but mathematically, of course, theta can keep on increasing and increasing and increasing. But because of the physics, we want to have the situation where this function here, the theta dependence, is actually periodic in theta with a period 2 pi. Otherwise, it would not map nicely onto the physics of the problem. Now, if we have the requirement that our function has a period of 2 pi, that automatically means that we have some additional requirements on k theta. K theta basically needs to be an integer. So either it is 0, in which case there's no dependence on theta. That's possible. That's an edge case. Or k theta is plus or minus 1, plus or minus 2, and so on and so forth. So these are the allowed values of k theta. And let's rename k theta L here. Now, if you recall, when we were deriving the Bessel differential equation for the first time, we basically did something similar to what we're doing here, but we forgot about the physics of the problem. So here, now we know about the physics, we can again do exactly the same derivation, and we can come to the conclusion that the function capital R has to satisfy a certain differential equation, Bessel's differential equation, obviously. So R squared, R double prime, R prime, and then we have R squared, K naught squared, N squared, and N, the refractive index, is a function of the radius, minus K Z squared minus L squared are equal to 0. So we have this equation here, but remember this equation is strictly speaking only valid in regions where the refractive index is constant or piecewise constant, and then you have solutions like these which are valid in each of the independent subregions, which you then still need to glue together. And that's basically what we're going to do here, is we're going to write down this equation for the core, the equation for the cladding, and then bring the results together in a way that satisfies Maxwell's equations. Now, for the core here, what's the stuff that differentiates the core from the cladding? Well, it's basically the refractive index. So in the core, we have n equal to n1. So we can redefine this constant here as, let's call that one kt1 squared. So 1, because we have index 1 in the core, is k0 squared n1 squared minus kz squared. And then for the cladding, we have a similar equation, but this time with another constant, kt2 squared, defined as follows. So this is just writing stuff here in a little bit more of a compact way, but there is also an exercise video which I encourage you to look at, which tries to interpret the physical meaning behind this kt1 and kt2. Okay, so now that we have this Bessel differential equation, we know that the solutions there are Bessel functions of a certain order, and the order in this case is L. And you see that the order here has everything to do with the angular dependence of the solution. So that gives you a physical interpretation behind the order of the Bessel function for our case here of looking at the eigenmodes of an optical fiber. So in general, in each region, we can write the solution either as a sum of the j's and the y's, or as a sum of Hankel functions of the first and the second kind. Or if you have a more rebellious streak, you can write it as a sum of j and h1 or y and h2. Doesn't really matter. So mathematically, all of these choices will be equivalent. But it turns out that if you make a really clever choice of two linearly independent solutions to the Helmholtz equation, that then, based on the physics of the problem, you can immediately already put one of those terms equal to 0. And that's very interesting because that will simplify our life enormously. So pause the video and see if you can figure out what a good choice would be to propose for the field in the core and for the field in the cladding, such that we can get rid of one of the terms that you need to propose. So in the core, we have fields that will be traveling around. So the field will also be traveling towards the interface and then reflect back. That reflected field will interfere with the forward propagating field or the outward propagating field. And that sort of suggests that we will be setting up standing waves there. And standing waves, that tells you something about the fact that we will have oscillating behavior. And that suggests something like oscillating Bessel functions, which are then the j's and the y's. So in the core, one might propose to say that the most general solution of the R dependence is a linear combination of Bessel function of the first kind of order L, kt1r, plus then a second term, which is the Bessel function of the second kind. Now, does this help us to already eliminate one of these two terms? Well, in this particular case, yes, because we know that this guy over here, Bessel function of the second kind, actually blows up at the origin. It diverges over there. And we know from the physics of the problem, if you measure the field that comes out of the core of an optical fiber, you will never have the situation that there's infinite light intensity at the very center of the fiber. So because of the physics of the problem, this term can never appear in practice. And therefore, that means that you only have a single term left, which is this one. So that simplifies our lives a little bit. And then we can try and play a similar game for the cladding. Now, for the cladding, we have the situation that if you have light which starts over here in the core, Perhaps at some point it leaks out towards the cladding, and then it will travel away towards infinity. But you will never have a situation where light from infinity will travel towards the core of the optical fiber to build up the field there. So you can write the field as sum of traveling waves, but the physics of the problem tells you that you only have an outgoing traveling wave. So now in the cladding, we're going to propose a solution of linear combination of Hankel functions. So Hankel function of first kind of order L, KT2 in the core, in the cladding rather, and then the Hankel function of the second kind, KT2R. And then, so we've already established that this guy corresponds to an outgoing traveling wave and this to an incoming traveling wave. There's no incoming wave, nothing comes back from infinity in our case, so we can put this term equal to 0. And then there's a little exercise you can do that say that you're dealing with a guided mode in the core, and then you can really show that this particular term here will correspond to an exponentially decreasing function, so that the field dies out at infinity, as you should expect from the physics of the problem. Good, let's take stock here. We know what we should propose for the field in the core and for the field in the cladding. So far, these have been two independent approaches. Now we need to bring these things together. We need to glue them together in such a way that the field at exactly the interface between core and the cladding satisfies all sorts of continuity equations that you can derive from Maxwell's equations. Now, what we're going to do is we're going to make our life a little bit easier here and say that the refractive index in the core is very similar to that one of the cladding. So this is a so-called weakly guiding index approximation. And then one can show, but we're not going to do that here, is that the continuity equations basically tell you that the function r should be constant, but also the derivative of r with respect to the little r coordinate should be constant as well. So pause the video and impose these conditions on those field solutions. Let's just look at what happens when little r is equal to big R, and then we fill that out here and there, and then the result should be the same. That's very trivial. That's just saying that A J L KT1 big R is equal to D H L2 KT2 of big R. Okay. For the derivative with respect to r, be aware of the fact that the function here is not a direct function of r, but a function of kt times r. So we need to use the chain rule. So for the chain rule, we first take the derivative with respect to the total argument, which is ktr, and then we take the derivative of the argument with respect to r. So if we do that, we get a. The derivative with respect to the total argument is denoted by a prime. That's the definition that we've also introduced earlier. And then the chain rule, taking the derivative of the argument with respect to r, will bring out an extra factor kt1 here. And then for the cladding, we have d kt2 hl2 prime kt2 capital R. Okay. So these conditions need to be fulfilled, and hopefully we can use those to figure out what A and D should be. One solution is that you put A and D equal to 0, but that's of course a very boring, trivial solution. We're not interested in a zero field. Are there any non-zero field solutions? Well, in order for that to be the case, then it should certainly be the case that this solution here is in essence that solution, but with just a scaling factor. Otherwise, it will not be possible to have a non-trivial solution here. So you can just divide these two and then impose that the result is equal. So if you divide the left-hand side, then you have JL KT1 capital R divided by KT1 JL prime KT1 1 capital R. And for the right hand side, we have HL2 KT2R, almost there, KT2 HL2 prime KT2R. So if this thing is true, then this equation is basically the same as that equation. You can just drop one, and that will allow you to have the situation that you can calculate A and D in a non-trivial way, that there's a non-trivial solution. Provided, of course, you first know what these guys are. And the question is, can you calculate these coefficients, so the J's and the H, from, for example, this equation over here? So here we have an equation, and the question is, how many unknowns do we have in this equation? But let's assume that we know the geometry of the waveguide, so that one is fixed. We know N1, we know N2, we know capital R, we know the wavelength at which we're operating, so everything is known except for perhaps a number of other terms, a number of other factors. The question is, how many unknowns do you have in this equation now? Now, naively, you might be tempted to think that there's two unknowns in this equation, namely KT1 over here and KT2 over there. That would spell trouble because you have one equation to figure out two unknowns. That obviously doesn't work. But luckily, if you go back to the definition of KT1 and KT2, you can see here that they're basically not independent, but they only depend on KZ. So as soon as you know KZ and you know the geometry of the problem, then you can calculate both K1 and K2. This equation over here, although it doesn't really look like this, is a single equation with a single unknown, and the unknown is the propagation constant Kz. So that works. You have this scary looking transcendental equation, which you perhaps solve numerically, and that will give you a number of allowed values for the propagation constant Kz. So once you know Kz, you go back to these equations over here, which will be guaranteed to be equivalent because of this condition here. So you only look at, for example, this equation over there. You know this factor and you know that factor, which means that you can also calculate the ratio of A and D. And that's all you need to know for the field profile, because remember, for the fields of an eigenmode, which we've written down like this, well, this field profile is only determined up to a scaling constant. So the only thing that you're interested in is the ratio between A and D. If you multiply the field with a certain constant factor, that's still a solution, exactly the same solution, exactly the same eigenmodes. So in a nutshell, this is how you can calculate the eigenmodes of an optical fiber, at least in the weakly guiding index approximation in the scalar case.